Hey everybody. You may notice the last video I was a little de-energized. So I came in on Saturday and a little more energized. So I want to talk to you about pressure. Then we'll talk about um some stuff about moles, dealing with weighted average, and we'll talk about solubility. Okay. Last time I mentioned pressure, 1 atmosphere equals 760 mmHg. There's also 760 torr, which is 101.3 kPa. Now, these are the ones you'll see. I'm also mentioning 14.7 psi. So, rethinking if we want to look at 2 atmospheres, let's make it 3 atmospheres. I want to examine 3 atmospheres as I convert it to kPa. Right? So you're looking at this, you're saying all I need to do is multiply 3 by 101.3. And yes, you'll be correct. But what I do want to do is set this up so we're consistent for when it gets a little tougher, and it's related to the same things we'll do in moles and stoichiometry. The unit on the top left is ATM, so I need to put unit top bottom right ATM. I am converted to kPa this time, so kPa goes on the top. Now I can look at, okay, there's 1 atmosphere. That's the number in front of atmospheres, and 101.3 kPa. The units of atmospheres drop out, and you're left with kPa. So if all you do is multiply what's on the top, divide what's on the bottom, you are correct when you say multiply 3 times 101.3 gets you the answer. So not a problem. I can also make this look like this. 3 ATM, ATM down there, kPa up there, 1 there, 101.3. So just a reminder, the bottom, where I put the multiplication symbol, the X, is what we're doing when we put the brackets, the fence, the railroad track. Okay, so nothing different. But looking to do a more difficult conversion, let's convert 13 100 millimeter Hg kPa. We want to start this same way, 13 mmHg. The unit on the top left is mmHg. The unit on the bottom right must be the same thing, mmHg. I'm looking for kPa, so I'll put kPa on the top. Good thing I like about pressure conversion is one little setup. So now I need to look for what are the numbers in front of kPa, what are the numbers in front of mmHg. According to our definition, there's 760 millimeters of mercury and 101.3 kPa. So I plug those numbers in. 760, 101.3 kPa. As in the past, we will multiply straight across, then divide by what's on the bottom, getting us our answer. Remember, it is up to you to get that answer. As you've noticed in class, I don't provide most of the answers. I'll help you set it up. That way you can do the final calculation. We could talk about if you answer right or wrong if you'd like. You must set them up and then also do the final calculation. If when I'm looking for your notes packet, I see that there are just the setups that I did, you don't get much points. Okay. Points come from setup and answer, not answer alone, not just setup alone. They must be together. So I want to briefly go over how we would use this with manometers. Okay. In this sample here, the gas is in the bulb, and we need to figure out who is pushing more. Is the gas pushing more, or is the um atmosphere pushing. After we figure out that piece of information, in this case, it looks like the gas is pushing more than the atmosphere. So pressure of the gas is greater than pressure of the atmosphere. The good thing about these kind of questions, normally this is given. So you just need to figure out what value is greater than the pressure of the atmosphere. To do that, you'll need the height, okay? And that's how we work these problems out. So let me find one of those problems in our notes packet. That's unit 4. Couple things you need to do. This has an open manometer like the one shown above. It's filled with mercury and connected to a sample of hydrogen gas. The mercury level is 78 millimeters high in the arm of the tube connected to the gas. If the air pressure is 98.7 kPa, what is the pressure of the hydrogen gas? Okay. Let me go back up. These are so this is an example. These are two of the same type of problems where if you look at the two you're looking at, the gas is pushing more than the atmosphere. So you add, but in this case, it says the mercury is higher on the side with the gas, which means that the atmosphere is pushing higher. So for this one, pressure of the gas is less than pressure of the atmosphere, which means to figure out the pressure of the gas, you take the pressure of the atmosphere and you subtract the height. So on next class, I'll be going over these. You will need to focus on pressure conversions for the test. Okay. In each of these is a conversion you need to do. So make sure you convert. I will work out the problems with you, but first you need to make sure each unit is in the correct thing. So in this problem right here, you need kPa. So you need to convert 78 millimeters of mercury into kPa. Then we can work on what to do, which means all you do is subtract your air pressure, 98.7 kPa, from your converted millimeters of mercury, and you'll get your answer. Okay. So didn't want to spend too much time on that one. All right. Now the other part is looking at these isotopes. All right. We found that hydrogen has 3 isotopes: protium, deuterium, and tritium. Most of the hydrogen that we are in contact with is protium. A little bit is deuterium, and even less of that is tritium. Tritium is radioactive, deuterium is heavy hydrogen and not usable for our bodies. So one of the things we do is we do what we call a weighted average. You'll notice that we've been talking about mass number, but on the periodic table, you will see decimal, which is interesting because we only talk about protons and neutrons, and those are items. So when you add up those items, you get a whole number. But when we deal with the abundance that exists in nature, we get what we call the average atomic mass. Okay. So in this case here, where the mass is on top, that's the abundance right there. So I take 12 multiplied by 98.7%. But to convert percent to a decimal, and remember we need to convert percent to decimal and work with it, I divide by 100. I take 13 next, times 1.1, divide that by 100. Then I take the next one, 14 times 0.0001. Divide that by 100. Yes, you'll notice it doesn't do much to your calculation. But then after you finish that, you take the sum of these three values. You do not divide after that. The only division you're doing is dividing it by 100. After that, you leave it alone. So you should have worked out these problems already. All right. The next thing I want to talk about molar mass is looking at how to calculate molar mass. So molar mass is pretty much the mass in the periodic table, but in grams per mole. That's the unit. If we're just looking at mass from the periodic table, that's atomic mass unit. But because we're looking at molar mass, that is grams per mole. So one of the things I look at is how many atoms of that element is present. I see magnesium and I see chlorine, but I see one magnesium and two chlorine. So this is molar mass. So we have to figure out the mass. Mass is found in the periodic table for elements. So I look for the mass of magnesium, 24.305. I look up the mass for chlorine, 35.453. I didn't multiply that out. I get 70.906 and 24.305. Multiply 1 times any number equals that number. Then I find the sum of these values. Okay. Now I do want to make sure we do one that is more complicated, like this one here, calcium nitrate. Let's see, calcium. Molar mass. Compound. So we're gonna do a difficult CaNO3. And there's two there. How about this one? VPO4, 5, and that's 3. You get these, you set these up correctly, you'll be fine. So in this case, I see calcium, see nitrogen, and I see oxygen. And parentheses, as in math, means I distribute or multiply. So I need to distribute or multiply to get my answer. So I need to distribute the two, the oxygen and the nitrogen. So there's one calcium, no number is there, so that means a 1. If we're going to write the element, that means there is 1 or more. Nitrogen, 1 times 2 gives me 2. Oxygen, 3 times 2, that's 6. So I'm going to multiply now by the mass from the periodic table. Calcium is 40.08. Nitrogen is 14.01. And because I'm rounding 2 digits after the decimal, it's a 16.00. I didn't multiply those numbers. I get 40.08. I get 28.02, and I get 48. Once again, I find the sum, and the unit is grams per mole, because I am using molar mass. Over here, I have vanadium, phosphorus, and oxygen. There's 3 vanadium, because that's the number that follows it. There's 1 times 5 phosphorus and 4 times 5 oxygen, which is gonna be 20 oxygen. I then multiply by the masses from the periodic table. Then I find the sum. I'm going to work out a problem from the notes packet. So this one, besides just having to figure out the molar mass, which you actually figure out on one of the questions 1 to 7. But because I didn't do those on this document yet, I'm going to actually do the whole thing. So I want to figure out how many grams are in 0.32 moles of phosphoric acid, H3PO4. So as in the past, 0.32 moles H3PO4. My railroad tracks. I have moles H3PO4 in the top left, mole H3PO4 needs to go in the bottom right. I'm converting to moles, so no, I'm converting to grams. But then I looked at that again. I just had moles. Converting to grams of H3PO4. So the one thing I don't have is the grams of H3PO4. If you did 1 to 7, you have it there. I don't on this document, so what I will do is quickly say H times 3, P times 1, O times 4, multiply by the mass. And then find the sum. Okay. And that number goes there. Oh, what number goes next to mole? The only number that goes next to mole, 1 for the next 2 units. After the next 2 units, we might change that. But we will change that. Okay. So that's the work with moles and stoichiometry. Set it up consistently. Set it up, and then you'll be fine. Last topic I want to talk about is solubility. Solubility. Of what we call a solution and how much dissolves at particular temperatures. Solution in 2 parts, a solute and a solvent. Solvent and a solute. You'll notice that the solute goes between the solvents. Okay. Always recommend that students write this kind of thought down so you can remember it. Also, the solvent is present in the greatest amount. Solute is present in the least amount. That's another way to think about it. We also talk about concentration. If we make a beverage that was dark and then wanted to lighten it up, we added water, we diluted. Which means the decrease ratio of solute in the solvent. That's diluted. Now we also mentioned the word molarity. Because we measure concentration in chemistry with molarity. Molarity has a formula to it. Molarity equals moles over volume. Volume is in liters. Okay. You're not responsible for this calculation in unit 3, but you will be responsible for this calculation in unit 4. So what are the other things to look at? I have this solubility chart. I have a value that is on the line. Anything on the line is considered saturated. Anything above the line is considered supersaturated. And therefore, anything below the line is unsaturated. So you need to know this for when there are different questions I might ask you. Is this value saturated, unsaturated, or supersaturated at this temperature? It's always at a specific temperature. Okay. So this is solubility chart, solubility curves. There's something really easy when you're looking at solubility curves. Temperature and the solute. 90% of all you have to do is look at the temperature and the solute. Let's say 50 milliliters of temperature of the water is 50. Let me start again. I'm sorry. Temperature of the water is 50 degrees Celsius, and the substance is KNO3. So 50 degrees, go all the way up to where you see KNO3. Then you read over to the left. At 50 degrees, KNO3 has 80 degrees dissolved. Okay. At 50 degrees, KNO3 has 80 degrees dissolved. I'm going to use that information right now. Need that information. That's 50 degrees. KNO3. There is 80 grams dissolved in 100 grams of water. That's the facts we have there. At 50 degrees, KNO3, 80 grams of solute dissolved. So one of the things that you will be asked, what if it's not 100 grams? What if the question says 300 grams? How do you figure that out? There's a ratio. How did you get to go from 100 to 300? What's your multiplier? It's going to be the same multiplier here to get your answer. You'll notice to go from 100 to 300 or 300 divided by 100 gives you 3. I have to multiply by 3. So I have to multiply over here by 3. Gives me that answer. There's another method. The other method is this. I'm going to take 100 grams of water, 80 grams dissolved. I'm looking for how much grams of water dissolves 300. I'm sorry. I'm looking for how many grams is dissolved in 300 grams of water. As some of you have told me, I'm going to cross multiply or do the butterfly. All right. So this looks like 100 times x is equal to 300 times 80. So to get the answer to isolate x by itself, I have to divide by 100 on both sides. So 3 times 8 above gives you 24 and another 0. So that's 240 grams. KNO3. When I do this one, I am going to cancel out those zeros and those zeros. Yes, you can do that. Oh, it's division. So 3 times 80, once again, x equals 240 grams. K. Now I'm going to take the same statement here, and I'm going to do a different problem. So what if it says 50 grams water? Whatever that multiplier is, it's the same multiplier for over here. Huh? So let's see. 80 grams, 100 grams of water equals, I don't know, over 50 grams. Once again, the butterfly cross multiply. So I will have 80 times 50 equal 100. X. Need to divide by 100. So I could take out a 10 from the 50 and a 10 from the 80, and I'll get 40. Okay. So I'm actually using my math. Okay. After I make it look like math, stop thinking chemistry. It is math. Use your math skill. You'll realize how it helps you out to differentiate the two. After it's set up like math, just treat it like math. There's no longer chemistry, and it works out. It is chemistry, but you have to use math rules to solve it. Okay? So that's about it. 2 videos, unit 3. Hopefully it helps. Later this week, I'll start recording for unit 4. Guys, have a good day.